Have you ever peered into the microscopic world of chemistry and wondered about the hidden forces driving some of its most dynamic, almost explosive reactions? What if I told you there's an entire realm where electrons don't just pair up neatly, but sometimes dance solo, driving rapid, powerful transformations fundamental to everything from the air we breathe to the plastics we use every day? Welcome to the Deep Dive, where we take your chosen sources and distill the most important nuggets of knowledge and insight, turning complex information into clear, compelling understanding.
And today we're taking a truly deep dive into a fascinating, dense chapter from Advanced Organic Chemistry, Part A, Structure and Mechanisms, 5th Ed. We're going to unpack the world of free radical reactions, those incredible processes involving molecules with unpaired electrons. Our mission, our sole purpose for this deep dive, is to clearly explain their core structures, intricate reaction mechanisms, key concepts, and surprising real-world applications in synthesis and analysis, all without getting lost in the weeds.
Yeah, and this isn't just abstract chemistry theory either. Understanding free radicals is, well, it's a real shortcut to grasping how some of the most vital chemical processes, both natural and industrial, actually work. You'll gain a well-informed perspective on everything from, say, how your body fights aging to how certain everyday materials are made. It's pretty fundamental stuff.
Absolutely. So what can you expect from our deep dive today? We'll go step by step, starting with the very basics, like what is a free radical, actually, and how these elusive intermediates are formed and detected. Then we'll delve into their surprising shapes and structures, and perhaps most importantly, we'll explore the unique kinetics and reactivity that make them so powerful in chemical transformations.
Okay, sounds like a plan. Ready to unpack this?
Let's do it. Here's where it gets really interesting.
All right, let's unpack this. When you hear radical in everyday language, it often means something extreme or revolutionary. And in chemistry, it's not that far off, is it? So what exactly is a free radical at its core?
Well, at its most basic level, a free radical is simply a molecule or an atom that contains at least one unpaired electron. That's it. This seemingly small detail is its defining characteristic, and it's why radicals are usually so incredibly reactive.
Okay, one unpaired electron. That makes them unstable, right?
Generally, yes. They aren't typically the starting compounds you'd throw into a flask, nor are they the stable products you isolate at the end. They're the fleeting, high-energy species, the intermediates, that pop up in the middle of a reaction to make things happen.
So they're not just hanging around. And how do they pop up? I mean, most of the reactions we talk about in organic chemistry involve electrons staying in pairs, right? Like a pair of electrons moves from one atom to another or stays put as a bond breaks. So how do radicals break those typical rules?
That's a crucial distinction. Most reactions are what we call heterolytic processes. That's where a bond breaks. But both of the bonding electrons stick together and go with one of the fragments. This often forms ions, a positive ion and a negative ion. Think of like an acid-base reaction, where a proton leaves without its electron and the remaining molecule takes both.
Right. One side gets both electrons, the other gets none. Hetero, meaning different.
Exactly. In radical chemistry, it's fundamentally different. We're talking about homolytic bond cleavages.
Homolytic, meaning equal splitting, right? So each electron goes its own way.
Precisely. When a bond breaks homolytically, each of the two bonding electrons goes to one of the fragments. So if you have a bond between, say, X and Y, and it breaks homolytically, you get X with one electron and Y with one electron, forming X dot and Y dot radicals. Our sources provide general examples of this, showing how you can form alkyl, vinyl, and aryl-free radicals through these homolytic processes. It's really about that clean, equal split of the bond.
That makes sense. It's about how the bond breaks evenly split. But are there other ways to form these elusive little guys besides just a bond splitting down the middle?
Yes, absolutely. While homolytic bond cleavage is very common, radicals could also be formed through something called atom abstraction. This is where an existing radical pulls an atom, often a hydrogen, from another molecule, leaving a new radical behind in the process.
Ah, okay. So it steals an atom and creates a new radical.
Right. Or they can be formed through one electron reduction or one electron oxidation followed by dissociation. So adding or removing just one electron can trigger bond breaking. These different methods give chemists, more precise control over how and when radicals are generated in a reaction.
Okay, they're often intermediates, as you said, meaning they don't just stick around. Which brings us to a key concept in radical chemistry: chain reactions. It sounds like they don't just react once, but they kind of reproduce themselves.
Exactly. Free radicals are very often involved in chain reactions, and this is where their real power and efficiency come from. A chain reaction is essentially a series of steps where a radical is continually regenerated, allowing it to start a new reaction cycle. It's like a chemical domino effect or a self-sustaining loop.
So not just one and done. The radical initiates, then somehow makes another radical to keep the reaction going.
Precisely. This sequence of regenerating reactions is called the propagation phase, and there are typically three distinct phases in any free radical chain reaction. First, you have initiation. This is the very first step where the reactive radicals are generated. For example, a molecule XY might break apart homolytically into X dot and Y dot radicals, kicking off the whole process. That's your spark.
Okay, the spark. Initiation gets it going. What's next?
Next is the propagation phase. This is the core repetitive sequence. Here, reactants are consumed, products are formed, and crucially, a new radical is regenerated to continue the cycle. Think of it like this. A radical A dot reacts with a molecule BC to form AB and a new radical C dot. Then C dot can react with another molecule, say AA, to form AC and regenerate A dot.
So A dot makes C dot makes A dot, and round it goes.
Exactly. This phase can repeat thousands, even millions of times, and the average number of repetitions defines what we call the chain length. The longer the chain, the more efficient the reaction overall.
And if something goes wrong, if the chain breaks, that must be termination.
That's the one. The final phase is termination. These are reactions that destroy reactive radicals, bringing the chain sequence to an end. This can happen when two radicals just bump into each other and combine, like two R dot radicals forming a stable RR molecule, or when a radical reacts with something else that effectively traps it without generating a new radical. It's the radical equivalent putting out the fire.
So initiation, propagation, termination. What are the key characteristics of these chain reactions then? What makes them unique in terms of how they behave kinetically?
Well, first, despite the low concentrations of the radical intermediates, the individual steps themselves often occur at remarkably high rates. They're incredibly fast at a molecular level. Second, as I just mentioned, the radical intermediates are typically present at very, very low concentrations because they react so quickly they don't build up. Third, the overall rate of the reaction depends on this delicate balance between the rate of initiation, how fast you make radicals, and the rate of termination, how fast you destroy them.
Right, the balance between starting and stopping the chains.
Precisely. If you initiate too slowly, the reaction might not get going properly. If you terminate too quickly, the chains will be too short, and the reaction won't be very efficient in making product.
And that chain length you mentioned, it's really important for the overall efficiency.
It's crucial. It specifies the average number of propagation sequences that occur per single initiation step. A long chain length means high efficiency, where a single radical spark leads to a lot of product formation before it's finally terminated.
That gives us a good framework for how they operate. Now let's talk about the actual moves these radicals make. The source mentions several fundamental types of radical transformations. What are these core chemical actions?
Yeah, there are three fundamental types of radical transformations that serve as the building blocks for more complex reactions. The first is atom or group transfer, which is very often called abstraction. This is where a radical pulls an atom, most commonly a hydrogen atom, from another molecule.
So like a radical Z dot plus a molecule RH becomes ZH plus a new radical R dot. The radical Z grabs a hydrogen, leaving a new radical R behind. This is a very common one, right?
Extremely common and synthetically very important. The source provides examples like a radical Z dot pulling a halogen X from Rx to become ZX and a new R dot radical. These abstraction reactions are key steps in many, many radical processes.
Okay, abstraction. What about adding to something? Like a double bond.
That's the second fundamental type, addition reactions. This is where a radical adds across an unsaturated bond, typically a carbon-carbon double bond or sometimes a triple bond. For synthetic purposes, additions to alkenes are particularly important because they're a great way to form new carbon-carbon bonds. And from a biological standpoint, their reactivity with molecular oxygen is incredibly significant, forming peroxy radicals, like C dot plus O2 yielding COO dot. We'll probably come back to that later.
Right, oxygen's role is huge. And finally, breaking things apart.
Yes, the third type is fragmentation reactions. These are processes where a radical breaks apart, usually spontaneously, into a smaller radical and a stable molecule. Most of these are what we call beta scission reactions, which means the cleavage of a bond that's beta to the radical site 2 carbons away.
Can you give us a quick example of a common fragmentation? Beta scission sounds specific.
Sure. A very common type is a decarboxylation, where a radical derived from a carboxylic acid, an acyloxy radical, loses carbon dioxide to form an alkyl radical. So you can picture RCO dot breaking apart to form R dot plus CO2. It's a way to simplify a molecule while generating a new radical. Other examples include decarbonylation, where an alkoxyl radical loses carbon monoxide, or alkoxy radicals fragmenting. These fragmentation reactions allow radicals to break down and create new, smaller radicals or stable molecules.
So extraction, addition, fragmentation, those are the fundamental dance moves of radicals. And once formed, what's their immediate fate? Do they just react with whatever's closest, or do they find a way to stabilize themselves quickly?
Pretty much the former. Most organic free radicals are very short-lived. They're so reactive that they typically undergo one of two very rapid reactions to find stability. The first is dimerization, where two radicals simply combine to form a stable, non-radical molecule. For instance, two R dot radicals combine to form an RR, simple coupling.
Two radicals meet, problem solved. And the second pathway?
The second is disproportionation. This is a bit more complex. It's where one radical transfers a hydrogen atom from its beta carbon, the carbon next to the one next to the radical, to another radical center. This results in the formation of one saturated molecule, an alkane, and one unsaturated molecule, an alkene.
Ah, so one radical gets reduced, the other gets oxidized, in a sense.
Kind of, yeah. For example, if you have two ethyl radicals, CH3CH2 dot, one might donate a hydrogen from its methyl group to the radical carbon of the other. This leads to ethane, CH3CH3, and ethene CH2CH2. This process is actually facilitated by weak bonds on that beta carbon, making that hydrogen transfer easier.
That paints a really clear picture of the fundamentals, what they are, how they react in chains, their basic moves, and their quick fates. Now, how do chemists actually find these things if they're so short-lived? It sounds like trying to catch smoke.
Huh? Yeah, I kind of feel like that for the early pioneers. The story of their discovery involves some truly clever detective work. Two early studies really stand out. The first was by Moses Gomberg around 1900. He was working with a compound called triphenylmethyl chloride and reacting it with silver metal. He observed some really unusual reactions in the resulting solution that simply couldn't be explained by normal ion-based chemistry at the time. He deduced that there had to be a triphenylmethyl radical, pH3C dot, present, even if only in tiny amounts, in equilibrium with a less reactive dimeric form, which turned out to be a cyclohexadiene derivative.
Wow, so he didn't directly see the radical, but inferred its existence from its strange behavior. It's quite a feat, especially back then, turn of the 20th century.
Exactly. The actual concentration of the free radical was incredibly small. The equilibrium constant was tiny, like 2 by 10 to 4 m. But its unique reactivity provided the first strong evidence for the existence of organic free radicals.
Incredible deduction. And the second key experiment.
The second pivotal set of experiments was carried out by Fritz Paneth in 1929. He was working in the gas phase, decomposing tetramethyl lead. He observed that the decomposition products, carried along by an inert gas stream, could remove a thin film of lead metal further down the tube. And, even more strikingly, they could then react further downstream to reform the original tetramethyl lead.
That sounds like a disappearing act and reappearing act all in one, like magic.
It really does. Paneth concluded that methyl radicals, CH3 dot, must exist long enough in the gas phase to be transported from the point of decomposition to the lead film, react there, and then potentially react again further on. This beautifully demonstrated that even highly reactive radicals like methyl could have a measurable, albeit short, lifetime under specific conditions.
So Gomberg and Paneth were the trailblazers, and since then our understanding has just exploded, especially with new techniques. But you mentioned most radicals are short-lived. Are there any that actually stick around for a while, like stable radicals?
That's a great question, and yes, there are some rare, fascinating exceptions. These are what we call long-lived or persistent free radicals. They resist the usual paths to self-annihilation, like dimerization or disproportionation, and can have significant lifetimes, sometimes existing for hours or even days under the right conditions. Our source material, Scheme 11.1, shows some captivating examples.
Like the triphenylmethyl radical, pH3C dot, that Gomberg first stumbled upon. Is that considered persistent?
Precisely. It's one of the classic examples. The key to its relative stability, and others like it shown in entries 1, 2, and 3 of that scheme, such as the perchlorinated version, is extensive delocalization of the unpaired electron into the aromatic rings. This delocalization spreads out the electron density over many atoms, making the radical center less concentrated and thus less prone to react with itself or other molecules. It's like spreading out a single charge over a large area, making it less intense at any one point.
So spreading out the electron makes it less aggressive, less reactive. What about sheer bulk? Can you just physically block the radical site?
Yes. Steric hindrance plays a huge role too. Look at entries 4 and 5 in Scheme 11.1, things like bis-T-butyl methyl, or even tris-T-butyl methyl radicals. Imagine these bulky T-butyl groups physically surrounding the radical center. They literally block other molecules, especially other radicals, from getting close enough to react and dimerize. This greatly slows down the dimerization rates.
Right, they just can't get close enough.
Exactly. Plus, some of these specific sterically hindered radicals lack the necessary beta hydrogens, which prevents the typical disproportionation reaction pathway from occurring. However, it's important to note that their persistence is often more about kinetic factors. They react slowly, rather than inherent thermodynamic stability. They can still be quite reactive towards, say, molecular oxygen, showing they aren't truly inert.
Okay, so delocalization and steric bulk. What about combining different types of stabilizing features, like delocalization and something else working together?
That's where we see synergistic conjugation. A classic example shown in the scheme is a radical called galvanoxyl, entry 6. It benefits from delocalization over its two aromatic rings, but also from the way its two oxygen atoms further distribute the unpaired electron through resonance. The two oxygens share the radical character. And again, the bulky nature of the groups attached near its oxygen atoms adds steric hindrance to the mix. It's like getting a double or triple dose of stability features working together. Another example, entry 7, benefits from ester and amino group interactions.
Right, synergy. And is there an ultimate stable radical, like a functional group that consistently forms stable radicals?
Yes. Probably the best example of a stable radical functional group is the nitroxide group, R2NO, shown as entry 8. The unpaired electron in a nitroxide is beautifully delocalized between the nitrogen and oxygen atoms. You can draw resonance structures showing the electron on either N or O. The actual NO bond order is somewhere around 1.5 between a single and a double bond. This intrinsic stability means that you can often carry out other chemical reactions, even ionic ones, on different parts of the molecule without affecting the nitroxide group itself.
That's amazing. So these nitroxides can basically serve as chemical tags, almost like stable labels, and you can still detect their radical character.
Precisely. They are incredibly useful as paramagnetic probes, especially in biochemical studies. Because they are stable enough, they can be incorporated into larger biological molecules like proteins or membranes, and their radical nature can still be detected, allowing scientists to study structure, dynamics, and interactions in really complex systems.
Okay, so those are the rare, long-lived ones. But most radicals are fleeting, as we said. How do chemists actually detect them? How do you catch that fleeting moment?
This is where powerful spectroscopic techniques come into play. The distinguishing characteristic of free radicals is their unpaired electron, which makes them paramagnetic, meaning they interact strongly with a magnetic field. The most useful and direct method for studying them is electron spin resonance, ESR, spectroscopy, also sometimes known as electron paramagnetic resonance, EPR, spectroscopy.
ESR, right. That rings a bell. It's kind of like NMR, but for electrons instead of nuclei, right?
That's an excellent analogy. ESR detects the transition of an electron between its different spin energy levels when it's placed in a strong magnetic field. When the sample absorbs microwave energy of the right frequency, the electron flips its spin state, and the spectrometer records this absorption. It's highly specific because only molecules with unpaired electrons will show an ESR signal. So if you see a signal, you know you have a radical.
Okay, so presence-absence is key. And like in MR, you get characteristic signals and maybe splitting patterns that tell you more.
Yes, absolutely. You get a characteristic G value, which is analogous to chemical shift in NMR. It tells you something about the electron's local electronic environment. But the real gold mine of detailed structural information comes from hyperfine splitting. This splitting arises from the interaction, the coupling, of the unpaired electron's magnetic moment with the magnetic moments of nearby nuclei that also have spin, such as hydrogen, proton, carbon-13, nitrogen-14, fluorine-19, phosphorus-31.
Hyperfine splitting, how does that work? How do you read the pattern?
The number of lines in the splitting pattern tells you how many equivalent magnetic nuclei are interacting with the unpaired electron. The rule is 2Ni plus 1 lines, where N is the number of equivalent nuclei, and I is the nuclear spin quantum number. For nuclei like hydrogen, C13, F19, P31, I is 12. So a single hydrogen splits the signal into a doublet, 2 lines. 2 equivalent hydrogens give a triplet, 3 lines. 3 give a quartet, 4 lines, just like an NMR splitting. Figure 11.1 in the source shows this visually.
Okay, so the number of lines tells you about neighbors. What about the size of the splitting?
The magnitude of the splitting, known as the hyperfine coupling constant, is even more powerful.
Yeah.
It's directly proportional to the amount of unpaired electron spin density actually present at the nucleus, causing the splitting. There's even an equation, the McConnell equation, A=Q, that relates the coupling constant A to the spin density on the carbon atom the hydrogen is attached to. Q is a proportionality constant. This allows you to actually map out where that single unpaired electron is spending most of its time on the molecule. It's like having a heat map for radical character.
Wow, that's incredibly detailed, like seeing electron distribution. Can you give an example?
Sure, figure 11.2 shows some great examples. For the benzene radical anion, the electron is equally distributed over all 6 carbons. The theory predicts a coupling constant of about 3.8 Gauss, and experimentally you see 3.75 Gauss with 7 lines because of the 6 equivalent hydrogens. It matches beautifully. For the ethyl radical, CH3CH2 dot, you see a complex 12-line spectrum. It's a triplet of quartets because the electron couples differently to the 2 alpha hydrogens and the 3 beta hydrogens. The coupling constants tell you exactly how much spin density is on each part.
That's powerful. So you can use ESR to really pin down the structure and electron distribution of even quite short-lived radicals.
Yes, but sometimes radicals are so short-lived they rearrange or react before ESR can even get a good look. The cyclopropyl-methyl radical is a classic case study of this challenge.
Right, you mentioned it rearranges quickly. What was the mystery there?
Chemists knew it was unstable and quickly ring opens to form the 3-butynyl radical. The question was how quickly, and could you ever observe the cyclopropyl-methyl radical directly? The experiment described involved generating the radical at very low temperatures by abstracting a hydrogen from methyl cyclopropane. Below -140 degrees C, they could clearly see the ESR spectrum of the cyclopropyl-methyl radical.
Ah, so cooling it down trapped it long enough.
Exactly. But as they warmed it up, even just above -100 degrees C, only the spectrum of the rearranged 3-butynyl radical was seen. At intermediate temperatures, they saw both. Crucially, cooling the 3-butynyl radical back down did not regenerate the cyclopropyl-methyl radical scastrums.
So the ring opening is fast and pretty much one way under those conditions.
It implies the ring opening is very easy, very facile, with an extremely short lifetime above -100 degrees C. Later studies measured the rate constant for ring opening at room temperature. It's incredibly fast, about 108 times per second. And interestingly, even though the equilibrium strongly favors the open form, they could detect reversible ring closure using isotopic labeling, showing the process could go backwards, just much more slowly.
What did computational chemistry add to this picture? Figure 11.3 is mentioned.
Computational models, using high-level MO and DFT methods, were able to calculate the energy barrier for the ring opening. The calculated barrier of about 8.5 kilovolt agreed really well with the experimentally estimated barrier of around 7.5 kiloball. These calculations also helped understand the rotational barriers in the radical compared to similar cations, providing a very complete picture of this dynamic system.
So direct detection with ESR is powerful, but you also mentioned a caveat earlier. If you don't see an ESR signal, that doesn't mean the radical isn't there, right? It could just be too fleeting.
That's a critical point to remember. ESR studies typically work with detectable, steady-state concentrations of radicals. If a radical is extremely short-lived or present in vanishingly low concentrations, you might not get a strong enough signal to detect it. Therefore, a failure to observe an ESR signal cannot be taken as conclusive evidence against a radical intermediate playing a role in a reaction mechanism. It might just be too fast or too low concentration for the technique to catch under those conditions.
So how do you catch those truly undetectable ones, the super fast ones that don't even register on ESR? Is there a trick?
For those, chemists use a very clever indirect technique called spin trapping. The idea is you introduce a non-radical molecule called a spin trap into the reaction system. This spin trap is specifically designed to react extremely rapidly with those short-lived elusive radicals. When it reacts, it forms a new, much more stable, and most importantly, paramagnetic species, which is often a nitroxide radical.
Ah, okay. So the trap basically reacts with the invisible fast radical and converts it into a stable, visible proxy radical that you can then study with ESR. That's a remarkably clever workaround.
Precisely. Once you have this stable spin adduct, usually a nitroxide, you can then analyze its ESR spectrum at your leisure. Because the structure of the stable nitroxide incorporates the original fleeting radical, it's attached to the nitrogen or carbon of the trap, its ESR spectrum provides indirect but often very detailed information about the structure of that original elusive species. It's like taking a snapshot of a blur by having it stick to something stable and then examining the sticky product.
That's brilliant, like chemical fingerprinting by proxy. Any other specialized detective techniques for spotting radicals in action?
Yes, another fascinating technique specific for radical processes is chemically induced dynamic nuclear polarization, or CIDNP. This one uses a standard NMR spectrometer, not ESR. What you observe is a strong, often very strange, perturbation of the NMR signal intensities for the products that are formed from certain types of free radical reactions. You might see signals that are much stronger than normal, enhanced absorption, or even signals that point downwards, emission, which is highly unusual in NMR. Emission signals in NMR. That sounds really weird. What causes that? It's a complex quantum mechanical effect, but basically it results when the normal population of nuclear spin states in the product molecules, which typically follows a Boltzmann distribution, is dramatically disturbed by the magnetic interactions that occurred within the radical pairs just before the product formed. The unpaired electron's magnetic moment messes with the nuclear spin populations, leading to this temporary overpopulation in either the lower or upper nuclear spin states, causing these strange, strong signals.
So if you see weirdly intense or upside-down NMR signals appearing during a reaction and then disappearing when it stops, it's a strong hint that radicals are involved in forming those products.
Exactly. Figure 11.4 shows an example with the decomposition of benzoyl peroxide. You see a clear emission signal for benzene, confirming it's formed via a radical process. When the reaction stops, the signal returns to normal absorption. It's a very sensitive technique, but it has limitations. Not all radical reactions show CAD&P effects, and sometimes minor radical pathways can produce prominent signals, so interpretation requires care.
Okay, so we have ESR for direct detection, spin trapping for the elusive ones, and CID&P is another clue. Now that we know how to spot them, how do chemists actually make these radicals reliably for study or for synthetic processes? What are the common starting guns to generate them?
There are several go-to methods, standard tools in the organic chemist's toolbox for initiating radical reactions. Perhaps the most common source are peroxides. Initiators like benzoyl peroxide, di-T-butyl peroxide, or T-butyl hydroperoxide are frequently used. They work because the oxygen single bond in peroxides is quite weak, typically around 30 kcal. This means you only need to heat them to relatively low temperatures, usually somewhere between 80 and 140 degrees Celsius, and that weak OO bond just snaps homolytically, making two radicals.
So you just heat them up gently and the OA bond breaks evenly, making two radicals. Pretty straightforward.
That's the basic idea. Depending on the peroxide structure, you get different radicals. Dialkyl peroxides decompose to give two alkoxy radicals, R true dot. Diacyl peroxides initially give carboxyl radicals, RCOO dot, but these often rapidly lose CO2, decarboxylate, to give alkyl radicals, R aldostific. Peroxyesters give a mix. One important note, though. Many peroxides are inherently unstable and can be explosive, especially if concentrated or impure. So extreme caution is always necessary when handling them in the lab. Safety first.
Absolutely. Good warning. What's another major way to get radicals going, maybe without peroxides?
A very general and often cleaner source is the decomposition of idosol compounds. These compounds contain a nitrogen double bond, address NN, flanked by alkyl groups. When heated or sometimes irradiated with UV light, they decompose to release a very stable molecule of nitrogen gas, N2, and form two carbon-centered radicals.
Ah, so you're basically forcing the molecule to split in half by ejecting a super stable small molecule like N2 gas. That seems like a strong driving force.
Exactly. The formation of N2 provides a significant thermodynamic push for the reaction. You can have symmetrical or unsymmetrical idosol compounds, allowing you to generate either one type of radical or two different ones. Adosobutyronitril, or AIBN, is probably the most widely used aduzo initiator. It decomposes reliably around 60-80 degrees C, forming nitrogen gas and two cyano-stabilized radicals, making it very convenient for many common reactions.
Okay, peroxides and azo compounds are big ones. What about other sources? Are there ways to make aryl radicals specifically?
Yes. For generating aryl radicals on a benzene ring, compounds called N-nitrosoanides are sometimes used. They undergo rearrangement and then decompose, releasing nitrogen gas and forming aryl and acyloxy radicals.
And organometallics. You mentioned Gomberg used silver. Can other metals or related compounds initiate radical reactions?
Absolutely. Organobranes, like triethylboron, are excellent radical initiators, particularly useful because they can work at very low temperatures. Their initiation mechanism usually involves a reaction with trace amounts of oxygen. This ability to initiate reactions at temperatures like -78 degrees C is invaluable for reactions involving temperature-sensitive molecules where you really want to avoid heating.
And one more specialized method mentioned in the source involves N-hydroxypyridine to thione derivatives. That sounds specific.
Yes, these acyl derivatives of N-hydroxypyridine 2-thione, sometimes called Barton esters, are quite versatile. They are prepared from carboxylic acids. When a radical initiator, like AIBN, is used, or sometimes just light, a chain reaction starts where a radical attacks the sulfur atom. This leads to fragmentation, releasing the pyridine-2-thione part and an acyloxy radical, which then rapidly decarboxylates to give the desired alkyl or aryl radical, R.U. This R. radical can then propagate a chain, making these useful for various transformations, like converting carboxylic acids into alkanes using a tin hydride, or into alkyl halides using a halogen source like BrCCl3.
Wow, quite a range of methods to generate these reactive species. So we know what radicals are, how to spot them, and how to make them. But what do they look like structurally? What are their preferred shapes? And how does that influence their reactivity? Let's dive into that.
Right, the structure and geometry of radicals is fascinating and has been a subject of intense study and some debate over the years. For the simplest alkyl radical, the methyl radical, CH3 dot, pretty much all the evidence from ESR, infrared spectroscopy, microwave spectroscopy, and high-level molecular orbital calculations consistently points to it being planar. The carbon atom and the three hydrogens all lie perfectly flat in a single plane. The carbon is essentially cis-p2 hybridized.
So methyl is flat, sp2 like a carbocation center. But what about more complex alkyl radicals with more alkyl groups attached? Do they stay flat or do they start to pucker?
For substituted alkyl radicals like ethyl, isopropyl, or T-butyl radicals, the situation changes. They are generally found to be slightly pyramidal, meaning the carbon atom at the radical center is slightly out of the plane defined by the three atoms it's bonded to. But here's the key. They have a very low barrier to inversion. Think of it like a very shallow umbrella that can rapidly flip inside out and back again.
So they're not rigidly pyramidal, they're floppy pyramids.
Exactly. And this degree of pyramidalization actually tends to increase slightly with more substitution. So the T-butyl radical is thought to be a bit more pyramidal than the ethyl radical.
Okay, so a T-butyl radical is more pyramidal than ethyl. Why is that? What stabilizes that shape?
The T-butyl radical has been studied extensively. Its slightly pyramidal structure is thought to be due to something called hyperconjugative interaction. Essentially, the half-filled p orbital on the radical carbon, the SOMO singly occupied molecular orbital, can interact constructively with the sigma bonds of the adjacent CH bonds in the methyl groups, but only if the radical center deviates slightly from planarity to allow a better orbital alignment. This hyperconjugation helps stabilize the radical, slightly elongates the CH bonds involved, and contributes to the observed pyramidal geometry. It also weakens those beta-CH bonds significantly, which is important for its reactivity, like disproportionation.
That's quite a detailed picture involving orbital interactions. What if you put really electronegative atoms directly on the radical center, like fluorine or oxygen? Does that push the geometry even more towards pyramidal?
Absolutely. The presence of sigma-donating substituents like fluorine or oxygen atoms attached directly to the radical carbon strongly favors an even more pyramidal structure. For instance, as you replace hydrogens with fluorines in the methyl radical series, CH3 dot, CH2F dot, CHF2 dot, CF3 dot, the radicals become progressively more distorted from planarity. The trifluoromethyl radical, CF3 dot, for example, is distinctly pyramidal, almost tetrahedral.
Why do electronegative atoms cause that? It seems counterintuitive, maybe.
There are a couple of reasons. First, lone pairs on the fluorine or oxygen atoms would repel the unpaired electron in the p orbital if it were planar. Pyramidalization moves the p orbital away, reducing this repulsion. Second, and perhaps more importantly, pyramidalization allows for better stabilizing interactions between the carbon's p orbital and the antibonding orbitals, sigma of the CF or CO bonds. This interaction effectively pulls some electron density towards the electronegative atom, which is favorable. Figure 11.5 actually shows a plot illustrating this trend nicely.
Okay, so geometry matters. Planar for methyl, slightly floppy pyramids for alkyl, more pyramidal with F for O. What about stereochemistry? This is crucial in synthesis. If a radical forms at a chiral center, a carbon with 4 different groups attached, does it retain its original configuration, its R or S identity, or does it lose it and become a mixture? Do radicals remember their origins stereochemically?
That's a fundamental question with big practical implications. If a radical formed at a stereogenic carbon were to become perfectly planar, or if it were pyramidal but inverted extremely rapidly, like that floppy umbrella, then it would lose its original stereochemical information. Reaction would occur from either face, leading to racemization and equal mixture of R and S products. On the other hand, if the radical were a rigid pyramid that didn't invert before reacting, it would retain its configuration.
And what does the experimental evidence tell us? Does it racemize or retain?
The overwhelming experimental evidence, shown in examples in Scheme 11.2 like chlorination, decarbonylation, fragmentation, and benzylic bromination, starting from chiral precursors, consistently shows that reactions generating simple alkyl radicals at chiral centers generally yield racemic products, or very nearly racemic products. This strongly indicates that simple alkyl radicals do not retain the tetrahedral geometry of their precursors. They either become effectively planar or, more likely, they are pyramidal, but invert so rapidly compared to the rate at which they react that they effectively lose their original stereochemical memory.
So for practical purposes, making a radical at a simple chiral center usually scrambles the stereochemistry. What about in really constrained systems like cyclic molecules or bridgehead carbons in bicyclic molecules?
That's where things get a bit more nuanced. In cyclic systems, like cyclohexyl radicals, inversion can still happen through ring conformational changes, and reactions often give mixtures of cis and trans products, again suggesting non-retention of stereochemistry, although sometimes subtle preferences are seen due to torsional effects or preferred attack trajectories.
Okay, but what about bridgehead systems? Those carbons in fused rings, like in adamantane. Carbocations, for example, really struggle to form there because they absolutely need to be planar, it's sp2 hybridized, and the rigid cage prevents that. Do radicals have the same severe problem?
That's a fantastic comparison, because bridgehead systems highlight a key difference between radicals and carbocations. Unlike carbocations, which are incredibly reluctant to form at bridgehead positions, reactions trying to form them are often millions or billions of times slower. Radicals can tolerate the geometric distortion imposed by a bridgehead position much better. While forming a radical at a bridgehead, like the 1 or Bornal radical, might be somewhat slower than forming a simple tertiary radical like T-butyl, maybe 500,000 times slower, this rate retardation is far less severe than the crippling 10-14 slowdown seen for SN1 reactions trying to make bridgehead carbocation.
So radicals are more flexible geometrically than carbocations. They don't need to be perfectly planar.
Exactly. They are okay with being pyramidal, and ESR spectra of bridgehead radicals confirm they adopt a pyramidal geometry at the bridgehead carbon. This tolerance allows radical reactions to occur at positions that are essentially off-limits for carbocation chemistry.
Okay, so alkyl radicals. Generally pyramidal, but invert quickly, racemizing stereocenters, but flexible enough for bridgeheads. What about unsaturated radicals like ally and vinyl? They have pi systems involved.
For unsaturated radicals, the story is slightly different due to the influence of the pi system. The allyl radical, CH2, CH2 dot, is expected to be planar to maximize the delocalization of the unpaired electron over all 3 carbon atoms through the pi system, and various experimental techniques confirm this planar structure.
Planar for ally makes sense for resonance. What about the vinyl radical, CH2CH dot? Is it linear, like you wouldn't expect for an hybridized carbon if it were a cation?
Nope. Experiment and theory both find that the simple vinyl radical is actually bent at the radical carbon, with a CCH angle around 137 degrees, not a 180. The geometry is influenced by substituent effects. Pi acceptors favor linear, pi donors favor bent.
Bent, okay. And does it invert easily? Can you separate E and Z isomers of vinyl radicals?
The barrier to inversion for vinyl radicals is very low, only about 0.2 kilocalmol. This means they interconvert between their different bent forms. Effectively, EZ isomers is substituted extremely rapidly. As a result, individual EZ isomers of vinyl radicals are usually very short-lived, and reactions proceeding through vinyl radical intermediates often give the same product mixture, regardless of whether you start with the E or Z precursor alkene, because the radicals interconvert much faster than they react.
Okay, that covers structure and shape. Now let's talk about stability. How do nearby groups, substituents, affect how stable a radical is? Does it matter if they're electron donating or electron withdrawing?
This brings us to substituent effects on radical stability, a really critical concept for predicting reactivity. We often quantify this stabilization using the radical stabilization energy, or RSE. What's particularly interesting and different from, say, carbocations, is that both electron-donating and electron-accepting substituents attached to the radical center can stabilize the radical. It's not just a one-way street.
That is different. For carbocations, electron-donating groups stabilize and electron-withdrawing groups destabilize. Why can radicals be stabilized by both types?
Radicals are electron deficient in the sense that they lack a full octet, so electron-donating groups help stabilize them through effects like hyperconjugation or resonance donation. However, they also have an unpaired electron in a relatively high-energy orbital, the SOMO. Electron-withdrawing groups, especially those with pi systems like carbonyls or cyano groups, can stabilize the radical by delocalizing that unpaired electron through resonance or inductive effects, effectively lowering the energy of the SOMO.
So both types of groups can interact favorably with the radical center. Does simple conjugation, like in allyl or benzyl radicals, provide significant stabilization?
Oh, absolutely. Conjugation is a powerful stabilizing factor. Allyl and benzyl radicals are significantly stabilized compared to simple alkyl radicals because the pi system allows the unpaired electron to be delocalized over multiple atoms. Table 11.1 in the source shows some BDE data reflecting this.
Yeah.
Interestingly, for allylic radicals, substituents at the 2 position, the middle carbon, are only slightly less effective at stabilizing than substituents at the 1 position, even though the simple resonance picture puts a node at C2. It shows the interactions are more complex.
Okay, conjugation helps a lot. But what about that special situation you hinted at earlier, where you have both an electron-attracting and an electron-donating group attached to the same radical site? Does that create a superstabilized radical?
Ah, yes. This is the fascinating phenomenon called captodative stabilization, sometimes also referred to as mirrostabilization. It refers to exceptionally strong stabilization that occurs when both an electron withdrawing, capto, and an electron donating, dative substituent, are present directly attached to the radical carbon center. They act synergistically, they mutually reinforce each other's stabilizing effects, leading to a much greater overall stabilization than the simple sum of what each group would provide alone. It's like a push-pull effect that strongly delocalizes the unpaired electron.
A push-pull effect. Are there clear experimental ways to see this synergistic effect in action?
Yes, there's compelling evidence. For example, by measuring rotational barriers in substituted allylic radicals, chemists found that the barrier drops significantly more when both capto and dative groups are present compared to just one type, indicating a stronger interaction and greater delocalization. Also, looking at bond dissociation enthalpies, BDEs, in certain molecules reveals dramatic drops when breaking a bond leads to a captodative stabilized radical. Some combinations, like a cyano group, capto, and an amino group, dative, lead to exceptionally low BDEs, indicating extreme stability for the resulting radical. Scheme 11.3 shows some examples, like radicals derived from Worcester salts or certain pyridinium salts, which can be highly persistent or even indefinitely stable in the absence of oxygen, demonstrating the profound power of this synergistic stabilization.
Wow, a stable radical based on push-pull. That's really counterintuitive, but powerful. We've talked mostly about neutral radicals so far, but what about charged radicals? Can an unpaired electron exist within an ion?
Yes, absolutely. Unpaired electrons aren't restricted to neutral species. They can exist in both radications, where a neutral molecule loses one electron, and radical anions, where a neutral molecule gains one electron. These are broadly called charged radicals.
Let's start with radical anions gaining an electron. How are they typically formed?
Radical anions are most commonly formed by the one-electron reduction of molecules with low-lying unoccupied molecular orbitals, especially aromatic hydrocarbons or conjugated polyunsaturated hydrocarbons. Classic examples involve reducing molecules like benzene, naphthalene, or anthracene using alkali metals, like sodium or potassium, in ethereal solvents, like THF or DME. These reactions must be carried out under strictly anhydrous and oxygen-free conditions, usually in product solvents like ethers, because any protons or oxygen would immediately react with and destroy the radical anion.
And how stable are these aromatic radical anions once formed? Do they stick around?
In the absence of oxygen or protons, solutions of these aromatic hydrocarbon radical anions can actually be quite stable, sometimes for long periods, often exhibiting deep colors. Their ease of formation generally increases with the size of the conjugated pi system. The more extensive the pi system, the lower the energy of the lowest unoccupied molecular orbital, making it easier to add an electron. Table 11.2 shows this trend, correlating reduction potentials with LUMO energies. Larger molecules are easier to reduce.
Okay. Bigger pi system, easier reduction. Any interesting exceptions?
Cyclooctane train, COT, is an E1. While it forms a radical anion, it has a particularly strong preference for undergoing a 2-electron reduction to form a dianion. This is because the COT dianion has 10 pi electrons, making it an aromatic system according to Huckel's rule for n+2, which provides significant extra stabilization.
Ah, the allure of aromaticity. So that's gaining an electron to make radical anions. What about losing one, forming radical-cation?
Radical-cations are formed by the one-electron oxidation of molecules, typically those with relatively high energy occupied molecular orbitals, haons. Aromatic hydrocarbons or alkenes can be oxidized, for instance, using strong chemical oxidants like antimony pentachloride, or sometimes via photoionization or electrochemically. Most simple radicalcations tend to have limited stability, often being highly reactive towards nucleophiles. However, ESR spectroscopy is still a powerful tool for characterizing their structures, even if they are transient. Just as ease of reduction correlates with LUMO energy, the ease of oxidation correlates with the energy of the HOMO. The higher the HOMO energy level, the easier it is to remove an electron and form the radicalcation. Table 11.2 shows oxidation potentials correlating with HOMO levels.
Okay, anions from reduction, antications from oxidation. Are there any charged radicals related to common functional groups, maybe like ketones?
Absolutely. A well-studied class are the kettles. These are radical anions formed by the one-electron reduction of carbonyl compounds, ketones or aldehydes. For example, reducing benzophenone with an alkali metal generates the benzophenone radical anion, a kettle, which is distinctively deep blue. Like many radical anions, it's highly reactive toward both oxygen and protons. A common reaction pathway for kettle radicals, especially if protons are available or concentrations are high, is reversible coupling, dimerization, to form a pinacool bianion, which upon workup leads to the reductive dimerization of the original carbonyl compound.
Okay, kettles from ketones. What about related dicarbonyl compounds?
Good question. One electron reduction of alpha dicarbonyl compounds, like biacetyl, gives radical anions known as semidiones. Closely related are the one electron reduction products of aromatic ketones, like benzoquinone, which are called semiketones. Both semidiones and semiketones are quite interesting. They can be protonated to give relatively stable neutral radicals. Importantly, both classes can be considered captodative radicals because they possess both an electron-donating group, like an oxygen atom or alkoxide, and an electron-accepting group, the carbonyl pi system, attached to or conjugated with the radical center. This contributes significantly to their stability and unique reactivity. They can be generated by reduction or sometimes even by oxidation of related compounds. ESR studies show extensive spin delocalization in these species.
We've covered the structure, stability, and character of radicals quite thoroughly. Now let's get into the really dynamic part. Their kinetics and reactivity in those chain reactions. How do these chains, which are so central to radical chemistry, actually behave in terms of their rates? What's their unique rhythm?
Yeah, the kinetic characteristics of free radical chain reactions are indeed unique, and they distinguish these reactions from many other types we encounter in organic chemistry. As we said, they are defined by those repetitive propagation steps.
Right, where one radical makes a product and regenerates another radical to keep the chain going, potentially thousands of times. So, how do you even derive a predictable rate law for something so dynamic involving these fleeting intermediates?
That's where a crucial concept comes in, the steady-state approximation. Because radical intermediates are generally so reactive and therefore present at very low concentrations, we can make a simplifying assumption. We assume that the rate at which these reactive intermediates are formed, mainly through initiation, is exactly equal to the rate at which they are consumed, mainly through termination but also propagation. Their concentration remains roughly constant or at a steady state throughout most of the reaction.
Okay, formation rate equals consumption rate. How does that help get a rate law?
Well, it allows us to express the concentration of the radical intermediate in terms of the concentrations of the stable reactants and the rate constants for initiation, key, and termination. For example, if initiation produces radicals at a rate proportional to some initiator concentration A2, say rate init equals Ka2, and the dominant termination involves two radicals combining, rate terms at equals 2 kdc.2, then at steady state, Ka2 equals 2 kdc.2. This lets us solve for the radical concentration. C is proportional to A2. If the overall reaction rate depends on a propagation step like rate equal Kpc reactant, substituting for C can lead to overall rate laws with fractional orders, like being half order in the initiator, or maybe 3/2 order in a reactant, which are hallmarks of many chain reactions.
3/2 order. That's definitely unique compared to simple first or second order reactions. But if termination reactions, like two radicals meeting, are often diffusion controlled and incredibly fast, how can the propagation steps even compete effectively to give long chains?
That's the key insight. While termination reactions are indeed intrinsically very fast, often limited only by how quickly two radicals can diffuse together, the concentrations of the radical intermediates are exceedingly low. This means the actual rate of termination, which depends on radical 2, can be relatively slow overall. This allows the propagation steps, which depend on radical X reactant, to compete effectively, especially since the reactant concentration is usually much, much higher than the radical concentration. It's a numbers game.
So we can potentially control or modulate the overall reaction rates by influencing either initiation or termination. That's where those initiators and inhibitors come back in, right?
Exactly. We already talked about initiators compounds like peroxides or AIBN that efficiently generate radicals to start chain sequences. By adding more initiator, you increase the rate of initiation, which generally increases the steady-state radical concentration and thus speeds up the overall reaction.
Makes sense. And then on the flip side, you have inhibitors, or what many people know colloquially as antioxidants. These are a big deal commercially, aren't they? Especially in things like food preservation and protecting plastics.
Or absolutely. They are of considerable economic and practical importance. Inhibitors, or radical scavengers, are compounds specifically chosen because they react extremely rapidly with the chain-carrying radicals, effectively trapping them and terminating the chain prematurely. This drastically reduces the chain length and thus slows down or even completely stops the overall radical chain reaction. Antioxidants are crucial for preventing unwanted free radical chain oxidations, a process often called autoxidation.
Autoxidation, that's the process that makes oils go rancid or degrades materials when exposed to air.
Precisely. It's the deterioration caused by reaction with atmospheric oxygen via a radical chain mechanism. Antioxidants are added to foodstuffs, petroleum products, polymers, rubbers, and many other materials to prevent this degradation. Common examples include compounds like BHT, butylated hydroxytoluene, and BHA, butylated hydroxyanisole used in food. Stable free radicals like galvanoxyl can also act as inhibitors in lab settings.
So what's their mechanism? How do common antioxidants like BHT actually stop that autoxidation chain?
The general mechanism for autoxidation involves an initiation step, forming R dot, followed by rapid reaction with oxygen, R dot plus O2 dot, ROO dot, forming a peroxyl radical, and then hydrogen abstraction by the peroxyl radical, ROO dot plus RH-ROH plus R dot. This last step forms a hydroperoxide, ROH, and regenerates the R dot radical to continue the chain. Phenolic antioxidants like BHT work primarily by donating their weakly bonded phenolic hydrogen atom to the chain-carrying peroxyl radical, RO dot, much faster than the peroxyl radical can abstract a hydrogen from the material being protected, RH.
So the antioxidant sacrifices itself to trap the reactive radical.
Exactly. ROO dot plus AROHR, ROO plus ARO dot. The resulting antioxidant radical, ARO dot, is usually much less reactive, often stabilized by resonance or sterics, and unable to effectively propagate the chain. Some antioxidants also work by decomposing the hydroperoxides, ROH, preventing them from breaking down later and reinitiating new chains.
And oxygen itself, molecular oxygen, plays this crucial dual role. It's essential for oxidation propagation, forming RO dot, but it also reacts rapidly with many other types of radicals.
That's right. Molecular oxygen, O2, is technically a biradical. It has two unpaired electrons in its ground state and is extremely reactive towards most carbon-centered radicals, ARC-O2. The reaction R dot plus O2-RO dot is often diffusion controlled or nearly so. This means that if you're trying to run a radical reaction without involving oxygen, you usually need to rigorously exclude air because oxygen can efficiently intercept your desired radical intermediates and divert them down an oxidation pathway, leading to unwanted oxygen-containing products.
Okay, that gives a good handle on the kinetics and control elements. Now, how do chemists actually put numbers to these reaction steps? How do you measure the speed of these fleeting species, their absolute rates, or at least their relative rates?
Measuring absolute rates for individual radical reaction steps can be quite challenging, often requiring specialized fast reaction techniques like laser flash photolysis. However, determining relative rates using competition methods is often much more straightforward and very commonly used.
Competition methods, how do those work? Sounds like pitting molecules against each other.
That's exactly what it is. The principle is quite simple. Suppose you have a radical A dot that can react with two different compounds, BX and BY, present in the same reaction mixture. A dot plus BX, AB plus X dot, rate constant Kx. A dot plus BY, AB plus Y dot, rate constant Ky. By measuring how much of BX and BY are consumed over the course of the reaction, usually by monitoring their disappearance using something like GC or NMR, you can determine the ratio of their rate constants, Kx, Ky.
Because they're both competing for the same limited pool of A dot radicals. The one that reacts faster will disappear faster.
Precisely. The relative consumption rates directly reflect the relative rate constants, provided the competing reactions are of the same kinetic order, which they usually are in these setups. You can even do intramolecular competition, comparing the reactivity of different sites within the same molecule, like abstracting a primary versus secondary hydrogen during chlorination. You just need to account for statistical factors, for example, number of hydrogens.
So competition gives relative reactivities, but sometimes you need the actual number, the absolute rate constant.
Yes, and thanks to advances in fast reaction techniques over the past few decades, chemists have been able to measure absolute rate constants for many fundamental radical reactions: hydrogen extractions, additions, cyclizations, fragmentations. Table 11.3 in the source lists some representative examples. Having these absolute values is critical for building accurate kinetic models and truly understanding fundamental reactivity patterns.
Now that we know how to measure their rates, let's really get into the heart of their behavior: structure-reactivity relationships. How does the structure of a molecule or a radical influence how fast it reacts, particularly in that key hydrogen abstraction reaction?
In hydrogen abstraction reactions like Z dot plus RH, ZH plus R dot cell, the single most important factor determining the reaction rate is usually the strength of the bond being broken, the RH bond in this case. This bond strength is quantified by the bond dissociation energy, BDE. Generally, the weaker the RH bond, i.e. the lower its BDE, the easier and faster the hydrogen atom is abstracted by the attacking radical Z dot.
So low BDE means easy abstraction. Where do we find weak CH bonds?
BDEs vary significantly depending on the structure. Table 11.4 provides a great overview. For instance, CH bonds adjacent to stabilizing groups like double bonds, allylic, triple bonds, propergelic, aromatic rings, benzylic, oxygen atoms and ethers or alcohols, or carbonyl groups are generally weaker than typical alkane CH bonds. Tertiary CH bonds are weaker than secondary, which are weaker than primary. Also, bonds involving heavier elements can be quite weak. Look at the group 14 hydrides. The SNH bond in tributyl hydride, Bb3SNH, has a BDE of only about 78 kilocamellia compared to around 93 kilocamolar for SiH. This makes tin hydrides exceptionally reactive hydrogen donors in radical reactions. Phenylselenyl, PHH, is even more reactive.
So bond strength is paramount. Does the solvent play a role in abstraction rates too?
Yes, solvent effects can be significant, although perhaps less dramatically than in ionic reactions. As mentioned earlier, the reactivity of the chlorine atom, for example, is noticeably attenuated when it forms a weak complex with aromatic solvents like benzene. There aren't as many comprehensive studies on solvent effects in radical reactions compared to ionic ones, but it's definitely a factor to consider.
Okay. And what does the transition state typically look like for hydrogen extraction? Is it linear?
The transition state is generally pictured as having the hydrogen atom partially bonded to both the donor carbon, R, and the abstracting radical Z, usually in a roughly linear arrangement, RHZ. To understand how structure affects the energy of this transition state and thus the reaction rate, we often invoke two fundamental principles: the Bell-Evans-Polanyi principle and the Hammond postulate.
Right, this came up before. Remind us how they apply here.
The Bell-Evans-Polanyi BEP principle basically says there's often a linear relationship between the activation energy, EA, of a reaction and its overall enthalpy change. For hydrogen abstraction, ARE is related to the difference in BDEs between the bond being broken and the bond being formed, ZH. So a weaker RH bond, making the reaction more exothermic or less endothermic, generally leads to a lower activation energy and a faster reaction. The Hammond postulate then relates the structure of the transition state to the reaction's energy profile. Highly exothermic reactions, like abstraction by a very reactive radical, tend to have early transition states that resemble the reactants. Highly endothermic reactions, like abstraction by a less reactive radical, tend to have late transition states that resemble the products.
Early TS for fast reactions, late TS for slow ones. How does this connect to the idea that reactive radicals are less selective?
It connects directly through the reactivity-selectivity principle, which is a cornerstone concept in understanding radical reactions. It states that, generally, the most reactive radicals are the least selective in choosing which hydrogen atom to abstract. The halogens provide the classic illustration, table 11.5. The fluorine atom is incredibly reactive. Abstractions are highly exothermic, leading to a very early reactant-like transition state with a tiny activation energy. As a result, fluorine atoms show almost no selectivity. They'll rip off pretty much any hydrogen they encounter. The chlorine atom is also very reactive, though less so than fluorine. Its abstractions are still generally exothermic, leading to relatively early transition states, and only modest selectivity between primary, secondary, and tertiary CH bonds.
Okay, F and Cl are reactive and non-selective. What about bromine? It's often used when you want selectivity, right?
Exactly. The bromine atom is significantly less reactive than chlorine. Hydrogen abstraction by Br dot is often endothermic or only slightly exothermic, especially for primary and secondary CH bonds. According to Hammond's postulate, this leads to a later, more product-like transition state, where the CH bond is substantially broken and the new HBr bond is substantially formed. In this later transition state, the stability of the forming carbon radical, R dot, plays a much larger role in determining the activation energy. Therefore, bromine atoms show high selectivity, strongly preferring to abstract hydrogens that lead to more stable radicals, tertiary, secondary, primary, and especially benzylic or allylic. Iodine is even less reactive, and H abstraction is usually too endothermic to sustain a chain.
So reactivity FClBrI and selectivity IBrClF. That makes sense. This selectivity is really useful synthetically, isn't it?
Immensely useful. For example, if you want to selectively functionalize the tertiary position of an alkane, bromination is the way to go. Or using reagents like N-bromosuccinimide, NBS, for highly selective allylic or benzylic bromination. The high selectivity of radicals like CBr3 dot or CCl3 dot, formed from CBr4 or CCl4, is even used in controlled halogenation of complex, sensitive hydrocarbons like cubane, where direct chlorination would be a mess.
Huh. Fascinating. Now, we saw earlier that radicals aren't purely neutral. They can have some polar character. Do we see polar effects influencing the rates of hydrogen abstraction reactions as well?
Yes, definitely. Although bond strength, BDE, is often the dominant factor, polar effects can play a significant and sometimes deciding role in reactivity and selectivity. It's observed that the rates of hydrogen abstraction by certain radicals correlate with the electron donating or electron withdrawing nature of substituents near the CH bond being attacked, much like in ionic reactions.
Can you give an example?
A classic example is a bromination of substituted toluenes. The reaction rate correlates reasonably well with the Hammond equation, giving a negative rho value, Anij 1.4. This indicates that electron-donating groups on the benzene rings speed up the reaction. This suggests that the transition state for benzylic hydrogen abstraction by the bromine atom has some polar character, with partial positive charge developing on the benzylic carbon, which is stabilized by electron-donating groups.
So radicals themselves can be thought of as having electrophilic or nucleophilic character.
Exactly. Radicals like the bromine atom, chlorine atom, or trichloromethyl radical, CCl3 dot, are relatively electronegative and behave as electrophilic radicals. They react faster with CH bonds that are more electron-rich. This often leads to negative rho values in Hammett plots. Conversely, some radicals, like the T-butyl radical, can behave as weakly nucleophilic, reacting slightly faster with electron-poor CH bonds, sometimes showing positive rho values.
Why do neutral radicals show these polar effects? Is it charge separation in the transition state?
It's thought to arise from some contribution of charge-separated resonance structures to the transition state, reflecting the electronegativity differences between the carbon, hydrogen, and the attacking radical. For example, R8Z might have minor contributions from structures like R plus HZ or RH plus NIDA-Z. However, interpreting these polar effects can be complex. Substituents affect not only the transition state polarity, but also the CH bond dissociation energy itself. Disentangling these factors requires careful consideration of electronegativity, polarizability, and bond energies. It's not always a simple correlation.
Right, multiple factors at play. Let's move to the next fundamental reaction type, addition reactions, especially radicals adding to double bonds. What are the general reactivity trends here?
In radical additions to alkanes, several factors influence reactivity. One trend is that highly delocalized radicals are generally less reactive in additions. For example, the phenyl radical, pH dot, is much more reactive towards adding to alkanes than the benzyl radical, PaCH2 dot, because the benzyl radical is already stabilized by resonance. Also, as we mentioned before, additions to aromatic rings are significantly slower than additions to simple alkenes because you have to disrupt the aromatic stabilization energy, which costs a lot energetically.
Okay, delocalization reduces reactivity. Do addition reactions also show that electrophilic versus nucleophilic character we just discussed for abstraction? Does the radical's nature matter relative to the alkane's substituents?
Yes, very much so. This is where polar effects often become quite pronounced and predictable in radical additions. Radicals like simple alkyl radicals, methyl, ethyl, T-butyl, and especially alpha-alkoxyalkyl radicals are generally considered nucleophilic. This means they react fastest with alkenes that bear electron withdrawing groups, EWGs, such as acrylates, acrylonitrile, or vinyl ketones. These EWGs make the alkene pi system electron-poor and thus more attractive to the nucleophilic radical.
So nucleophilic radicals like electron-poor alkenes, what about the opposite, electrophilic radicals?
Electrophilic radicals, such as those bearing electron withdrawing groups like fluorine, example CF3 dot, or carbonyl groups, behave oppositely. They react fastest with alkenes that are electron-rich, meaning those bearing electron-releasing groups, ERGs, like alkyl groups or alkoxy groups.
So nucleophilic radicals prefer EWG alkenes, and electrophilic radicals prefer ERG alkenes. It's about matching the radical's character to the alkene's electronics. How does frontier molecular orbital FMO theory explain this? Figure 11.6 is relevant here.
Frontier molecular orbital, FMO theory, provides a very elegant explanation for these polar effects in radical additions. It focuses on the interaction between the radical's singly occupied molecular orbital, SOMO, and the alkene's frontier molecular orbitals, the highest occupied molecular orbital, HOM, and the lowest unoccupied molecular orbital, LMO. The key idea is that the reaction rate is favored when the energy gap between the interacting orbitals is small. For a nucleophilic radical, which has a relatively high-energy SOMO, the dominant interaction is between its SOMO and the alkene's LUMO. Electron-poor alkenes with EWGs have low-energy LUMOs, leading to a small energy gap and fast reaction. For an electrophilic radical, which has a low-energy SOMO, the dominant interaction is between the alkene's HOMO and the radical's SOMO. Electron-rich alkenes with ERGs have high-energy HOMOs, again leading to a small energy gap and fast reaction.
It's all about minimizing that SOMO-LUMO or HOMO-SOMO energy gap for the best interaction. That makes intuitive sense. Does this FMO picture also predict where the radical adds on an unsymmetrical regiochemistry?
Yes, it often does. The interaction is typically strongest where the orbital coefficients, which represent the electron density in that orbital, are largest. For most alkenes, both the HOMO and LUMO have larger coefficients on the terminal beta carbon than the internal alpha carbon. This explains why radical additions usually occur at the less substituted carbon beta addition, forming the more substituted and often more stable radical intermediate on the alpha carbon.
So FMO explains both the rate enhancement from polar matching and the regioselectivity. Does the transition state for addition look more like reactants or products?
Radical additions to alkenes generally have relatively early transition states, meaning the TS structure still resembles the starting radical in alkyl. This is supported by observations like the fact that the rate of addition of the T-butyl radical to various alkenes correlates strongly with the alkene's LUMO energy, figure 11.7, which is a ground state property of the alkene.
So the reaction decides how fast to go based mostly on the starting material's properties. Table 11.7 shows some data.
Yeah, exactly. Table 11.7 nicely illustrates these trends, comparing the reactivity of methyl, cyanomethyl, and hydroxymethyl radicals towards different substituted alkenes. You can see the influence of both the radical's nature and the alkene's substituents, including the significant rate enhancement caused by alpha fluorosubstituents on the radical.
Computational studies must be useful here too.
Immensely. Calculations can map out the potential energy surfaces, determine activation barriers, and predict regioselectivity for additions to various unsaturated groups, not just CC, but also CO, aldehydes, ketones, CNN, alkenes, and others. For example, calculations show that addition of methyl radical to formaldehyde or ampenes is competitive with H abstraction, while addition to nitrones is highly favored. For CO and CAN, addition usually occurs at the carbon atom. Figure 11.8 even shows how barriers for alkyl radical addition to aldehydes change with radical structure.
Okay, that covers addition well. Now let's talk about building rings using radicals. Radical cyclizations. These are super important in organic synthesis, right, for making cyclic molecules.
They absolutely are. Radical cyclizations are a cornerstone of modern synthetic strategy, particularly for forming 5- and 6-membered rings. While the source notes that the synthetic applications covered in more detail in Part B of the book, understanding the kinetics and selectivity of these cyclizations is crucial for mechanistic studies as well. The rates of certain well-characterized cyclization reactions often serve as useful radical clocks to time other competing radical reactions.
Radical clocks, like the cyclopropylmethyl radical ring opening we discussed earlier.
Precisely. That ring opening, entry 30 in table 11.3, is extremely fast and well-calibrated, serving as a benchmark. Another fundamentally important cyclization is the 5-hexanyl radical cyclization, entry 33. A radical on a 6-carbon chain with a double bond at the end preferentially cyclizes to form a 5-membered ring, a cyclopentyl radical, rather than a 6-membered ring, a cyclohexyl radical.
Wait, it prefers forming a 5-membered ring exocyclization even though a 6-membered ring might seem more stable thermodynamically? Why is that? Is this related to Baldwin's rules?
Exactly. This strong preference for 5-exocyclization over 6-endocyclization is a classic example of kinetic control governed by stereoelectronic factors, essentially a radical version of Baldwin's rules. It comes down to the preferred trajectory of approach. For the radical center SOMO to effectively overlap with the alkene's pi antibonding orbital to form the new sigma bond, it needs to approach at a specific angle, around 109 degrees ideally, but practically more like 70 degrees relative to the pi plane. When you consider the constraints of the connecting alkyl chain, achieving this optimal geometry is much easier for the transition state leading to the 5-membered ring, 5-exotrig, than for the one leading to the 6-membered ring, 6-endotrig.
So the geometry of the transition state is just easier to achieve for the 5-exo path, making it faster, even if the 6-membered ring product might be slightly more stable.
That's the generally accepted explanation. Table 11.8 shows calculated and observed preferences, confirming that 5-exo is strongly favored over 6-endo, which is roughly comparable in rate to 6-exo, forming a 6-membered ring via attack at the internal carbon, while 7-endo is typically disfavored.
Do substituents affect this preference?
Yes, substituents can influence both the rate and the regioselectivity. Steric hindrance, near the radical or the double bond, can slow down cyclization. Electronic effects can sometimes alter the regiochemical outcome. For example, placing an electron withdrawing group, like an ester, on the double bond can sometimes promote 6-endo cyclization more than usual. Conformation also plays a role, as seen in cyclizations involving acyl radicals, figure 11.9, or those forming larger rings, figure 11.6, where specific conformers might favor one pathway over another.
Fascinating interplay of kinetics, geometry, and electronics. Okay, we've covered abstraction, addition, and cyclization reactivity. What about some of those other important radical reactions mentioned earlier, starting with fragmentation reactions? How fast are they?
Fragmentation rates vary widely depending on the specific reaction. We already mentioned acyloxy radical decarboxylation, RCOO.R. plus CO2. This is generally extremely fast, often with rate constants around 106 to 109 alpha 1, especially for simple alkyl-oxy radicals. This means it's very difficult for an acyloxy radical to do anything else before it loses CO2.
So decarboxylation is almost instantaneous. What about peroxide decomposition itself? Does the structure influence how fast peroxyesters break down?
Yes, the rate of thermal decomposition of T-butyl peroxyesters, which form R dot and CO2 and TBUO dot, is strongly dependent on the structure of the R group. This dependence indicates that the alkyl-carbonyl bond cleavage is involved in, or occurs very shortly after, the rate-determining OO bond cleavage step, especially when R dot is a stable radical.
And alkoxy radical cleavage, like T-butoxy radical breaking down.
Alkoxy radical fragmentation, like CH3,3CO dot, CH3 dot plus, CH3,2CO, is another important fragmentation. The rate of this beta scission process is primarily determined by the stability of the alkyl radical, R dot being eliminated. More stable radicals are eliminated faster. Competition studies, like the one correlating fragmentation versus H abstraction shown in figure 11.11, confirm this strong dependence on radical stability.
What about acyl radical decarbonylation, RCO.R.more plus CO? Is that as fast as decarboxylation?
No, decarbonylation is generally significantly slower than decarboxylation. Its rate also strongly depends on the stability of the R dot radical formed. For instance, forming a highly stable tertiary benzylic radical can happen extremely fast, 108S1, whereas losing CO from the benzoyl radical to form the phenyl radical is much slower, 1S1. This means decarbonylation can sometimes compete with other radical reactions like halogen atom transfer. Fragmentation of radicals derived from ethers or acetyls also occurs, but often slow enough for additions to compete.
Okay, fragmentation rates depend heavily on structure. Now let's pivot back to free radical substitution reactions. We discussed the principles of halogenation earlier with reactivity selectivity. Let's flesh that out with specifics.
Right. For halogenation, substituting H with X, the thermochemistry is absolutely key, summarized in figure 11.12. Fluorination, using F2, is violently exothermic for almost all steps. It's very difficult to control, non-selective, and can even cleave CC bonds, not generally practical for selective synthesis. Iodination, using I2, has an endothermic hydrogen abstraction step, RH plus I dot to R dot plus HI. This makes it energetically uphill, and the overall chain reaction cannot usually be sustained. Direct iodination via radicals is rare. This leaves chlorination and bromination as the workhorses for radical halogenation. Both have propagation steps that are overall exothermic, allowing chain reactions to proceed feasibly.
And as we discussed, bromination is the selective one.
Yes, bromination typically shows high selectivity. The initial H abstraction by Br dot is often the rate-limiting step and is sensitive to the stability of the R dot radical formed late transition state.
Yeah.
This leads to preferential reaction at tertiary, allylic, and benzylic positions. In bromosuccinimide, NBS, is a particularly useful reagent for selective allylic and benzylic bromination. It works by maintaining a very low, steady-state concentration of Br2, which favors the radical substitution pathway over competing ionic addition of Br2 to the double bond.
And chlorination is the less selective, more reactive option.
Correct. In chlorination, using Cl2, the H abstraction steps by Cl dot are almost always exothermic, leading to an early reactant-like transition state, Hammond postulate. This makes the reaction less sensitive to the stability of the product radical, resulting in lower selectivity between primary, secondary, and tertiary CH bonds. Chlorination also shows significant polar effects because the chlorine atom is quite electrophilic. It tends to avoid abstracting hydrogens near electron withdrawing groups. Succativity can also be influenced by solvents. Complexation of Cl dot by benzene, for instance, makes it slightly less reactive and more selective.
Are there ways to get intermediate selectivity?
Yes, using reagents like T-butyl hypochlorite, TBuOCl, utilizes the Tb-toxy radical, TBO dot, as the hydrogen abstractor. This radical is less reactive than Cl dot, but more reactive than Br dot, giving intermediate selectivity. For example, tert dot sec dot pri reactivity ratio is around 60.10.1. Scheme 11.4 shows various examples illustrating these different halogenation methods.
Okay, that covers halogen substitution. What about oxygenation, specifically autoxidation? We touched on inhibitors, but let's look at the process itself.
Right. Autoxidation is the free radical chain oxidation of organic molecules by reaction with molecular oxygen, O2, typically from the air. The basic mechanism we outlined before holds. Initiation -R dot, propagation 1, R dot plus O2 - RO dot, very fast. Propagation 2, RO dot plus RH dot, ROH plus R dot, often rate limiting. Termination steps consume radicals.
So the rate-limiting step is often the hydrogen abstraction by the peroxyl radical, RO dot dot. What makes a molecule susceptible to autoxidation?
The ease of autoxidation is primarily governed by the rate of that hydrogen abstraction step, propagation 2. Alkyl peroxyl radicals, RO dot dot, are fairly selective radicals. They preferentially abstract hydrogens that are relatively weak or lead to stabilized carbon radicals. Therefore, positions like benzylic, allylic, tertiary CH bonds, and CH bonds alpha to ethers or amines are particularly susceptible to autoxidation because the resulting R dot radical is stabilized.
Can you give some examples of where autoxidation is important, both industrially and maybe as a hazard?
Industrially, the large-scale oxidation of cumin, isopropyl benzene, to cumene hydroperoxide, which is then cleaved to produce phenol and acetone, is a major process relying on autoxidation. The oxidation of aldehydes to carboxylic acids is another common example, driven by the facile abstraction of the formal CH bond. And the critical lab hazard we mentioned, ethers, especially cyclic ones like THF or open-chain ones like diethyl ether, are notoriously prone to autoxidation of the CH bond alpha to the oxygen. This forms alpha hydroperoxy ethers, which can decompose explosively, especially when concentrated. It's a serious safety issue.
A very important reminder. Now let's shift gears slightly to free radical addition reactions. We discussed the principles and polar effects. What about adding specific reagents like hydrogen halides?
Again, thermochemistry rules the day here, figure 11.39. Radical chain addition of HF or HI to alkanes is generally not observed because at least one of the propagation steps is significantly endothermic, breaking the chain. HCl addition is borderline. The H abstraction step, R dot plus HCl dot RH plus Cl dot, is slightly endothermic or thermoneutral, making the chain inefficient and polymerization often competes. But HBr addition is a classic exception. Both propagation steps, Br dot plus alkane, Wr dot R dot plus HBr dot RH plus Br dot, are exothermic. This allows for an efficient radical chain process.
And this is the reaction that gives the anti-Markovnikov product, right? Explaining that old puzzle.
Exactly. The bromine atom adds first to the less substituted carbon of the alkene double bond beta addition, because this forms the more substituted and generally more stable carbon radical intermediate on the alpha carbon. The subsequent hydrogen abstraction by this radical leads to the overall anti-Markovnikov addition product, where H adds to the more substituted carbon and Br to the less substituted carbon. This discovery resolved the apparent violation of Markovnikov's rule observed when reactions were initiated by peroxides or light.
And the stereochemistry. Is it syn or anti-addition?
HBr addition generally favors anti-addition, where the H and Bro add to opposite faces of the original double bond, especially in cyclic systems. Bridged radical structures were once proposed, but recent computational work suggests a trans-like transition state for the addition step, followed by H abstraction that is faster than rotation around the newly formed CC bond, leading to the observed anti-stereoselectivity.
Okay, HBr is special. What about adding halomethanes like carbon tetrachloride, CCl4, or bromotrichloromethane, BrCCl3?
These additions are some of the oldest known preparative radical chain reactions. The chain typically involves abstraction of a halogen, usually Br from BrCCl3 or sometimes Cl from CCl4, by an initiating or propagating radical, generating a CX3 dot radical, your example CCl3 dot. This CX3 dot radical then adds to the alkene, beta addition again, and the resulting radical abstracts a halogen from another molecule of the halomethane to continue the chain. Reactivity generally follows the CX bond strength, CBr4, BrCCl3, CCl4. These are useful for adding CX3 groups across double bonds. Stereochemistry is often mixed in flexible systems, but transientity addition can be preferred in rigid systems due to steric factors. These reactions can sometimes be catalyzed by transition metals like iron or copper.
Can other carbon-centered radicals add, like from aldehydes?
Yes, acyl radicals, RCO dot, can be generated by H abstraction from aldehydes. These radicals can add to alkenes in a chain process to form ketones. Acyl radicals tend to be nucleophilic. Intermolecular additions are also possible, forming cyclic ketones. Adding formamide to alkenes can form primary amides.
What about sulfur compounds? Do thiols add easily?
Yes, thiols, RSH, and thiocarboxylic acids undergo very general and efficient radical chain additions to alkenes. The SH bond is relatively weak, making H abstraction easy, and the resulting thiol radical, RS dot, adds readily to double bonds. Both propagation steps are usually exothermic, leading to efficient chains. The addition typically shows anti-Markovnikov regioselectivity. Sulfur adds to the less substituted carbon, and often favors anti-addition stereochemistry, though sometimes less selectively than HBr scheme. The Merge report 11.5 provides a good collection of examples for these various addition reactions.
Okay, lots of addition chemistry. We also mentioned halogen, sulfur, and selenium group transfer reactions. How do those work? It's not just H abstraction.
Right. This involves the abstraction and transfer of atoms or groups other than hydrogen. A key example is iodine atom transfer. For instance, treating a 6-iodoalkene derivative with an initiator can lead to cyclization. The initially formed carbon radical abstracts iodine from the starting material, forming the cyclized product and propagating the chain via an iodine atom carrier. Selenium group transfer using aryl selenides, PHAR, is also very effective. Photolysis or radical initiators can generate radicals that add to alkenes. The resulting radical can then abstract the PHE group from the starting material, propagating the chain and leading to beta-seleno derivatives or cyclized products. Tin hydrides can be used in conjunction to reduce the intermediate radical before transfer, leading to overall hydroselenation.
Interesting ways to move heavier atoms around. What about moving hydrogen atoms within the same molecule? Intramolecular hydrogen atom transfer.
These are particularly powerful reactions because they allow for the functionalization of CH bonds that are relatively remote from the initial site where the radical is generated. The key feature governing their selectivity is a strong kinetic preference for the hydrogen abstraction step to occur via a six-membered cyclic transition state. This means a radical will preferentially abstract a hydrogen atom from a position that is geometrically accessible through such a six-membered ring, typically from the delta carbon, C5, the radical is C1.
A six-membered transition state is preferred. Can you give a classic example?
The Hofmann-Loeffler reaction is the archetype. Photolysis of an N-halamine in acidic solution generates an iminium radical-cation. This radical then abstracts a hydrogen atom from the delta position via six-membered TS. The resulting carbon radical is then trapped by halogen transfer, leading to a delta halamine, which spontaneously cyclizes under the reaction conditions to form a pyrrolidine ring, a five-membered nitrogen heterocycle. Similar reactions with N-halamides can lead to lactones. You can also see transannular hydrogen abstraction in medium-sized rings, where a radical formed on one side of the ring reaches across to abstract a hydrogen from the other side, again often via a pseudo-six-membered TS.
Very elegant remote functionalization. Finally, let's touch upon rearrangement reactions of free radicals. We know carbocations are famous for rearranging. 1-Bernoulli shifts. Do radicals do that readily?
Generally, no. Rearrangements involving the migration of simple saturated alkyl groups, like a 12,2 alkyl shift, are much less common and usually much slower for free radicals compared to carbocations. This is because the transition state for such a shift in a radical would involve a three-membered ring with 3 electrons in the bonding-antibonding orbitals, a bridged radical, which is energetically unfavorable compared to the 2-electron bridge transition state in carbocation rearrangements.
So simple alkyl shifts are rare, but what can migrate in radical rearrangements?
The groups that typically migrate in radical reactions are usually unsaturated substituents, such as aryl groups, phenyl-vinyl groups, or acyl groups. The mechanism for these migrations is different from a simple shift. It usually involves an intermolecular addition of the radical center to the pi system of the migrating group, forming a transient bridged or cyclic radical intermediate, which then reopens in a different way to give the rearranged radical. For aeromigration, this intermediate resembles a cyclohexadenal radical.
Are these migrations fast?
They vary. Phenyl group migration, a 12-2 shift, is generally quite slow, but can be observed, especially if promoted by steric crowding at the initial radical site. Phenyl and acyl group migrations can be faster, sometimes proceeding through intermediate cyclopropyl carbonyl or cyclopropoxy radicals, respectively. Computational studies, like figure 11.15 for acyl migration, have helped clarify these pathways and barriers. Alkenyl or cyano group migrations are typically even slower. Scheme 11.6 shows some examples where these rearrangements have been observed.
So rearrangements happen, but are more limited and involve specific migrating groups compared to carbocations. That wraps up the core reactions and mechanisms. What's the big picture here?
So what does this all mean for you, our listener? Well, from those early historical discoveries by Gomberg and Paneth that first hinted at their existence, to the sophisticated spectroscopic techniques like ESR and spin trapping that let us capture their fleeting moments, all the way to the intricate interplay of structure, stability, and reactivity that dictates their reaction pathways. Free radicals are truly a fundamental and fascinating cornerstone of advanced organic chemistry.
Yeah, they really are. And they're not just theoretical curiosities. As we've seen, they are right at the heart of so many industrially significant processes, from the production of polymers and plastics that make up so much of our modern world, to methods for fine chemical synthesis.
Absolutely. And beyond industry, they play crucial roles, both good and bad, in biological systems involved in processes like aging and tissue damage, but also essential for certain metabolic pathways and cellular signaling.
We've seen how a relatively small toolkit of fundamental reaction types, abstraction, addition, fragmentation, and the less common rearrangements combine in these powerful, often highly efficient chain mechanisms. This allows chemists to achieve transformations that might be difficult or impossible using other types of chemistry.
And understanding that subtle balance between initiation, propagation, and termination, and critically, how factors like substituents, bond strengths, and stereoelectronics influence radical stability in reaction pathways, that's what allows chemists to predict, control, and harness these incredibly dynamic processes for useful purposes.
It really is a testament to the elegance and complexity of molecular interactions, that something as simple as a single unpaired electron can open up such a vast, powerful, and fascinating world of chemical reactivity.
It certainly is. There's always more to learn and discover in chemistry, and the world of free radicals, despite being studied for over a century, is still ripe for continued exploration and new applications.
Well said. Thank you for joining us on this deep dive into the world of free radical reactions. We hope you found these insights valuable and maybe even sparked a new curiosity about these invisible, highly energetic forces that shape so much of our chemical world.
We invite you to consider what other deep dives into the fascinating world of chemistry or other complex topics you'd like to embark on with us next time.